The enigma of KIC 8462852a celestial beacon shrouded in speculation. The cosmos, a canvas of infinite black punctuated by the glittering dust of ancient light, has always served as the ultimate repository of the unknown, a vast expanse challenging the very limits of human comprehension, and within this boundless theater, one particular stellar anomaly has captured the scientific imagination with an intensity rarely seen since the first tentative whispers of extrasolar planets first broke the surface of astronomical discourse, the star designated KIC 8462852, often abbreviated to KIC 8462852, or simply Tabby star, after the lead researcher who first brought its baffling characteristics to the forefront of mainstream astrophysics, Tabitha S. Boyajian. This star, nestled approximately 1,470 light-years away in the constellation of Cygnus, presented an observational paradox that defied conventional stellar physics, compelling astronomers to consider explanations that bordered on the extraordinary, ranging from the mundane but complex, like dusty cometary swarms, to the truly radical, such as megastructures built by an advanced extraterrestrial civilization. The initial unraveling of this mystery began not with a grand, dedicated observation, but as a byproduct of the Kepler Space Telescope's primary mission, to discover exoplanets by monitoring minute dips in a star's brightness, a technique known as the transit method. Kepler, operating between 2009 and 2014, diligently watched tens of thousands of stars, including KIC 8462852, expecting to catalogue the occasional, regular, and predictable dimming caused by an orbiting planet crossing the stellar disk, which typically results in a fractional decrease in luminosity, often less than 1% for an Earth-sized planet transiting a Sun-like star. KIC 8462852, a G-type main-sequence star slightly larger and hotter than our own Sun, initially seemed unremarkable, catalogued as a standard target. However, the light curve derived from KIC 8462852 began to screen deviation, broadcasting a signal so statistically improbable that initial automated flagging systems likely dismissed it as instrumental noise or systematic error. The data, when subjected to rigorous human scrutiny, revealed not the gentle, periodic dips characteristic of planetary transits, but a series of bizarre, aperiodic, and massive decreases in brightness. These were not mere flickers, these were profound occultations. In the most dramatic recorded event, the star's light dimmed by an astonishing 22%, a staggering occlusion that suggested an object, or collection of objects, of unprecedented size was passing between the star and the Kepler observatory. If this obscuration were caused by a single, opaque body, its diameter would need to rival a significant fraction of the star's radius, an object so large it strains credulity within the known parameters of natural stellar system formation. Furthermore, the occultations were utterly irregular. They did not repeat on a set schedule, they were sporadic, lasting from a few days to several weeks, before vanishing, only to reappear weeks or months later with entirely different magnitudes of dimming. The sheer scale of the dimming immediately ruled out most common astrophysical explanations. A single, large exoplanet, even one approaching the size of Jupiter, would only cause a dimming of less than 1% for a star of KIC 8462852 size. Even a large brown dwarf transiting edge-on would struggle to achieve such deep dimming unless the alignment was impossibly precise and the object impossibly large relative to the star's apparent size from Earth. The regularity demanded by Kepler's transit methodology demands precision, and KIC 8462852 offered chaos, a stochastic signature that defied the ordered clockwork predicted by Newtonian mechanics applied to typical planetary or stellar debris disks. The scientific community, fueled by the detailed analysis published by Boyajian and her colleagues, rapidly converged on hypotheses, dividing themselves into two broad camps: the naturalistic explanations, rooted in conventional astrophysics, and the exotic, often sensationalized, extraterrestrial hypotheses. The naturalistic explanations primarily focused on vast, dense clouds of material orbiting the star. The leading candidate within this category involved cometary fragments, perhaps ejected from a distant Oort cloud analog due to gravitational perturbations from unseen distant companions or even the tidal forces of the Milky Way's spiral arms interacting with the system over vast timescales. If a massive swarm of comets, perhaps tens of thousands or even hundreds of thousands of icy bodies, were to disintegrate or collide in a chaotic orbital path across the line of sight, the cumulative effect could produce the observed deep, irregular dips. However, this model faced immediate challenges. The sheer mass required to produce such persistent and deep obscurations via cometary debris would necessitate a far more gravitationally dynamic system than typically observed, and the debris cloud itself should, over time, begin to dissipate or settle into more regular, predictable orbits through gravitational focusing, unless the system was actively being perturbed. Furthermore, the spectral signature analysis, or lack thereof, began to play a crucial role. When an object transits a star, it can subtly alter the light spectrum passing through its atmosphere if it possesses one, or reflect light if it is illuminated. For KIC 8 for 62852, follow-up observations, notably those conducted using ground-based telescopes like the Large Binocular Telescope and specialized facilities such as the Vanderbilt University's Dyer Observatory, sought to detect infrared (IR) excess. Dust, particularly warm dust relatively close to the star, should re-radiate absorbed starlight in the infrared spectrum. If the dimming were caused by a massive, opaque structure, the structure itself might emit heat detectable in the infrared. Initial comprehensive surveys, specifically those targeting the near-infrared and mid-infrared using instruments like the Spitzer Space Telescope, yielded a crucial, albeit complex, result. There was a slight, statistically significant, elevation in infrared emission, particularly in the 2.4 micron wavelength band, suggesting the presence of some form of warm particulate matter, consistent with dust. However, this IR excess was relatively mild, insufficient, by itself, to account for the deep 22% occlusions if the dust were distributed evenly in a typical disk structure. The dimming events were far too opaque and transient for a standard, passive debris disk. This led to refinement of the natural hypothesis that fragmenting planetary system or the massive, recently disrupted swarm. Consider a protoplanetary disk or a much older, mature system where a large planetary body, perhaps a Neptune or even a Saturn-sized planet, had experienced a catastrophic tidal disruption event, breaking apart into trillions of smaller, irregularly shaped chunks. These fragments, now orbiting in highly eccentric or chaotic paths, would periodically intersect the line of sight to Earth. This scenario could explain the aperiodic nature and the massive dips, as large clusters of debris pass across the stellar face. The required mass, while still immense, was conceivably achievable through the gravitational stripping of a large outer planet. Yet, even this required a mechanism to maintain such extreme dynamical instability over the tens of thousands of years the star has been observed by Kepler, an instability that should eventually damp out through mutual gravitational interactions, leading to either accretion or ejection of the material. The inherent physical difficulty with all purely natural explanation stems from the observed depth versus the lack of corresponding significant IR excess during the deepest dips. If the obscuring material were simply gas and dust, the ratio of light blocked in the optical or visible spectrum to the light blocked in the infrared should conform to known blackbody radiation physics for a given temperature. The KIC 8 for 62852 data suggested an occultation event that was absorbing visible light far more efficiently than expected for a cloud of warm dust at that proximity, or perhaps an incredibly cold, extremely dense structure absorbing almost no thermal energy, which is counterintuitive for any large, naturally occurring aggregate in space. This statistical anomaly and the sheer audacity of the dimming pattern pushed the scientific discourse toward the fringe, or rather, toward the highly speculative but rigorously logical realm of the Kardashev scale, specifically Type II civilizations capable of harnessing the total energy output of their parent star. This is the realm of the Dyson swarm or Dyson sphere concept, first popularized by physicist Freeman Dyson. A Dyson swarm is not necessarily a solid, rigid shell, which presents insurmountable engineering problems due to tidal forces and material stress. Rather, it is envisioned as a vast, intricate network of independent solar energy collectors, orbiting the star in intricate, yet non-interfering, configurations, designed to capture the maximum possible fraction of the star's total luminosity for energy needs, communication, or computation. If KIC 8 for 62852 were orbited by such a structure, or, more plausibly, a partially constructed or defunct Dyson swarm, the observational data would manifest exactly as seen: massive, irregular shadowing events as the massive collectors or structural elements drift through the observational plane. The notion gained significant traction precisely because it offered a compelling explanation for the specific combination of high opacity and aperiodicity. A partially completed structure, perhaps undergoing construction, failure, or deliberate reconfiguration by its builders, would naturally produce these chaotic, deep dips. Furthermore, while the IR excess was noted, it was relatively small compared to what a fully active, waste-heat radiating Dyson sphere would generate. This suggested either a civilization utilizing energy transfer mechanisms far more efficient than predicted by current terrestrial thermal dynamics, or, more likely, a partially deployed structure that was not yet radiating significant waste heat across the entire stellar surface area, or perhaps a Dyson bubble designed for shade rather than total energy capture. The speculation intensified when SETI researchers, notably those associated with the Breakthrough Listen initiative, directed powerful radio telescopes, including the Green Bank telescope, toward KIC 8 for 62852. The goal was to search for narrowband radio signals, the hallmark of artificial, intentional communication or leakage from advanced technological processes. While initial exhaustive searches yielded nothing definitively artificial, the mere fact that a star exhibiting such bizarre photometric behavior was prioritized for intense electromagnetic surveillance underscored the profound shift in scientific perception this single star induced. It moved KIC 8 for 62852 from an interesting astrophysical puzzle to a prime target in the search for techno-signatures. To further constrain the possibilities, researchers turned to higher-resolution spectroscopic analysis during subsequent dimming events, if observable. The objective was to search for absorption lines indicative of specific elemental compositions or atmospheric pressures characteristic of engineered materials, or even the presence of complex molecules that might point toward industrial activity. The challenge here lies in the transient nature of the event. Capturing a high signal-to-noise ratio spectrum during a deep dip requires exceptional preparation and the right orbital mechanics aligning perfectly with terrestrial observation windows. While initial spectroscopic data provided strong evidence for the star itself being a relatively normal G-type star, showing no unusual spectral anomalies indicative of an active stellar engineering project like stellar lifting or controlled fusion manipulation, the lack of an observable atmosphere on the occulting object remained a key observation. A massive cloud of dust or gas would likely show discernible absorption or emission features. The fact that the obscuration appeared largely opaque suggests a solid or near-solid surface blocking the light, reinforcing the megastructure hypothesis, or a remarkably homogeneous, extremely opaque dust cloud. Let us consider the physics of light blockage in more detail to underscore the severity of the problem. Stellar luminosity, $L, is related to the radius of the star, $R_, and the luminosity of a unit area, $B, by the Stefan-Boltzmann law integrated over the surface area, though for simplicity in transit calculations, we often focus on the geometric blocking factor. If a portion of the light, $L_OBS, is observed when the star is partially occulted by an object of area $A_OC, the fractional dip $Δ L is proportional to $A_OCT_, assuming uniform intensity across the star's disk, which is not entirely accurate due to limb darkening. Limb darkening dictates that the edges of the star appear dimmer than the center. A deep dip like 22% suggests a very large occulting area, or multiple smaller areas overlapping effectively. If the material is distributed like a swarm of small objects, the probability of them lining up perfectly to produce a deep, single-event dip is exceedingly low unless they are gravitationally bound into a very dense, coherent structure or are following highly synchronized, yet dynamically unstable, orbits. The aperiodic nature and dynamical stability. The hallmark of the KIC 8 for 62852 mystery remains its aperiodicity. Natural systems tend towards predictable orbital mechanics governed by Kepler's laws and subtle relativistic or tidal perturbations. Even a chaotic debris field, while irregular, usually exhibits statistical clustering that allows for predictive modeling over longer timescales. The dips in KIC 8 for 62852 seem genuinely random within the observation window. This randomness strongly favors an engineered system where the components are either maintained in position by active station-keeping systems, or where the sheer volume of independent structural elements ensures that a random alignment, rather than a periodic one, is the dominant observable feature from our distant vantage point. Imagine a scenario where the civilization is deliberately maneuvering the swarm components, say, solar collectors the size of small asteroids, to optimize energy collection or communication alignment with other stellar systems or even within their own local network. Such maneuvering would necessitate constant adjustments, resulting in exactly the kind of irregular brightening and dimming observed. This interpretation transitions the problem from one of astrophysics to one of advanced engineering and artificial intelligence management systems controlling astronomical scale infrastructure. Further evidence, or rather the persistent lack thereof, also merits discussion: the lack of observed periodic modulation at shorter timescales, which would be expected if the obscuring material were a typical dusty disk where individual clumps or planetesimals orbit relatively closely. The observed events are long and deep, suggesting large contiguous structures or very dense aggregations of material passing over a relatively short observational period compared to the system's orbital mechanics. The gravitational signature challenge. A critical test for any massive structure or large swarm orbiting KIC-8 for 62852 would be its gravitational influence. If a planetary mass object or a dense collection of massive objects were present, we should theoretically detect minute wobbles in the star's position, the radial velocity method, or subtle shifts in the transit timing variations, TTVs, if smaller orbiting bodies were present. High-precision radial velocity measurements of KIC-8 for 62852 have been conducted, but thus far, they have not conclusively demonstrated the presence of massive, close-in companions that would be required to dynamically sculpt a debris field into the observed configuration, nor have they detected the gravitational signatures associated with an artificially maintained, massive swarm structure. This absence of clear gravitational perturbation is perhaps the strongest argument against the most massive interpretations of the Dyson structure hypothesis, yet it is not entirely disqualifying. A swarm composed of numerous smaller components, each perhaps the size of a terrestrial planet or less, but totaling a significant fraction of a Jupiter mass, might distribute its gravitational influence in a manner that is difficult to detect above the background noise of stellar activity or instrumentation limitations over the relatively short baseline of current observations. Moreover, if the civilization employs localized gravity manipulation, a capability far beyond our comprehension, the gravitational signature might be entirely masked or engineered to appear benign. Extending the time horizon, a multiband search. The study of KIC-8 for 62852 cannot remain confined to the optical domain. Future investigations will critically rely on next-generation infrared observatories, such as the James Webb Space Telescope, which possesses superior sensitivity in the mid-infrared compared to Spitzer, allowing for more detailed characterization of any thermal emissions during dimming events. If the civilization is employing large solid structures composed of non-ideal black bodies, materials engineered for high thermal conductivity or specific radiative properties, these differences should manifest in the infrared spectrum, potentially distinguishing them from natural silicate dust clouds. The goal is to isolate the spectral fingerprint of the occulting body. If the material shows spectral features inconsistent with rock or ice, perhaps indicating metallic alloys or complex artificial polymers, the case for technosignatures strengthens immeasurably. Furthermore, the search must extend into longer observational periods. The Kepler mission observed only a few years of the star's activity. Over decades or centuries, even a highly chaotic system should reveal patterns, or conversely, remain stubbornly chaotic, which itself is a significant data point. If KIC-8 for 62852 continues to exhibit random, deep dimming over the next 50 years, the probability that this phenomenon is driven by non-random, controlled processes increases logarithmically, provided that the star itself is confirmed to be dynamically stable against internal perturbations like pulsations or magnetic cycles which could mimic dimming, though the observed dips are far too large for typical stellar variability. The possibility of stellar engineering presents an even more profound level of speculation. Beyond the Dyson swarm, theories propose stellar-scale engineering projects designed to alter the star's output for terraforming distant worlds or for propulsion drives. Concepts like stellar light sails pushed by focused energy beams, or even controlled stellar lifting to alter the star's composition over eons, would leave photometric signatures far grander than those observed at KIC-8 for 62852. However, the observed dimming is consistent with occlusion, the blocking of light, rather than an intrinsic change in the star's radiative output, which favors structures passing in front of it. The ongoing debate within the astrophysics community reflects a fundamental tension between conservatism and open-minded scientific inquiry. the principle of mediocrity suggests that the laws of physics are universal and that natural explanations, however complex, should always be prioritized until proven impossible. This conservative approach dictates that the debris field model, perhaps involving a highly eccentric, massive object perturbing a distant asteroid belt, must be exhausted before invoking intelligences operating on Kardashev Type 2 scales. Yet, the data resists simple accommodation within the established models of planetary system evolution. No known natural process comfortably explains the combination of 22% dimming, long duration, and absolute aperiodicity observed in KIC8 for 62852's light curve without invoking extremely rare, fine-tuned initial conditions that seem almost as improbable as intelligent design. In conclusion, KIC8 for 62852 remains one of the most compelling astronomical anomalies of the 21st century. It serves as a profound reminder that the universe is not obligated to conform to our current understanding of planetary dynamics or debris evolution. Whether the true explanation lies in a spectacular, unprecedented natural cataclysm, a stellar system ripping itself apart in a fashion never before witnessed, or in the majestic, silent testament to intelligence harnessing stellar energy on a scale we can barely visualize, KIC8 for 62852 continues its silent vigil, broadcasting a photometric signal that challenges us to either refine our models of cosmic chaos or finally acknowledge the possibility that we are not alone in building structures among the stars. The next decade of observation, particularly with enhanced infrared capabilities, will determine if this stellar enigma resolves itself into a dusty footnote in the annals of stellar variability, or if it marks the first tentative whisper of a technological civilization rewriting the known limits of astronomical possibility. The sheer longevity and depth of the mystery ensure that KIC8 for 62852 will remain a focal point, a celestial Rorschach test upon which humanity projects its deepest hopes and most profound scientific questions regarding its place in the vast, indifferent cosmos. The data continues to accumulate, layer by layer, seeking the true architect of these strange shadows, a search that probes the very boundary between the natural and the artificial in the grand architecture of the galaxy.